Okay, so our next speaker is Harald Servat, and he's going to present on the migration of OpenACC-based applications into OpenMP 5+.
Thank you for the introduction, Sarah. So yes, well, we'll skip the disclaimer this time. Let's go for the topic. So I assume that I don't have to explain you about OpenMP and OpenACC, but thing is that both of languages are almost the same. Possibly a few of you may disagree with that, but it's evident that if one looks into the directives in both languages, it's quite evident that in many situations at least, similar syntax has similar semantics. So it means that some constructs in OpenACC are very similar to that in OpenMP. And that is something that one may take into consideration when it has to the deal of how to convert one to another, right? If we look back in history, if I remember correctly, OpenMP was started discussing first regarding on the offloading before then OpenACC was created. But it is true that OpenACC has attracted more developers. Basically, that was because of the OpenMP offloading appeared after OpenACC. In fact, there was this discussion first. And OpenACC was able to adopt advanced features at faster rate than OpenMP, right? And that would be also explained by the fact that they were always simply focusing on a specific hardware like GPUs, while OpenMP is able to consider other target mechanisms like FPGA, right? But it is true that also that OpenMP has become more attractive to users, developers, and rest of the community, right? Because several reasons. First is that the features that OpenACC has also been either had an equivalent in OpenMP or have been surpassed in terms of functionalities or flexibility. It is also true that the compiler folks, we have seen that a number of there's a wider adoption in compilers regarding the OpenMP. Not only compilers, but also hardware vendors, right? So, and the fact that the OpenMP not only supports GPUs, so that is a thing that that personally I believe that this has made the people to consider OpenMP as an alternative to OpenACC. Thing is that we know that there are a number of applications out there written in OpenACC, and thing is, how can we help these people, these developers, on turning their OpenACC applications into OpenMP, right? So, related work, I refer to different alternatives. Most of them are either focused on C or in Fortran, right? The thing is that while we are working on the conversion from some customers' applications from OpenACC to OpenMP, we were discussing, can we get some sort of automatized mechanism that we can convert these applications to something that we can use? And we came up with this integration tool for OpenACC to OpenMP API. And excuse me, but we had to choose something like that because of branding naming, which basically helps on converting valid OpenACC applications, either written in Fortran or in C or C++, into OpenMP 5 applications, right? The idea is the tool only provides for semantic equivalent translation and for I would say, the commonly used subset of OpenACC directives that are typically seen in most of the applications, right? So this is an ongoing effort. We know that there are a plethora of applications out there, and we are happy to hear about requests and suggestions on whether API calls or whatever, whether OpenACC constructs that are not supported at these days. The tool is open source, and you can go and download, and you can either submit requests or comments or whatever. So this is something that we are working on. The important thing I would like to highlight here is that the end of the tool is to try to generate the best possible OpenMP translation for the application, but we cannot guarantee the best performance. And the reason is quite simple. So there are too many hardware accelerators out there. There are too many runtimes out there, and there are too many compilers out there, right? So it's difficult to try to get the best for all of those. And it is also true that some OpenACC performance-related clauses cannot be portable from one to the other, right? So for performance, I would strongly suggest to use performance analysis tools. For instance, the one we saw before in the previous presentation. I know that their team on Mellor.com is working on their tool, but you can also use many others like Bitune or Scalaska or Parabear. Why not? Right. So the two main points for the tool beyond the support for C and Fortran is the fact of that we took advantage of OpenMP 5 for successive versions of the specification. And I think that the big thing here is the usage of the loop construct, right? When I was reading the related work, it was not obvious when one had to convert this Pragma ACC parallel loop that we have on the left, and we have some nested loops, how to translate that when using this Pragma OMP target teams distribute parallel 4. So where is the best place to put the target teams or the distribute or the parallel 4? Maybe you need a SIMD inside. So it's not that evident which is the best transformation here. But if we look into if we consider the loop construct, that it's pretty comfortable for the translation, right? It's very easy to automatize from the OpenACC into the OpenMP, right? It's a natural translation one-on-one here. The other one, which is, it's not a dramatic improvement here, but is the fact that the support for the present or default present in OpenMP 5. OpenMP 4 could not mimic the exact behavior, so one could play with the alloc clause on the alloc on the map clause, right? But it's not exactly the same because the present basically checks for the availability of that pointer into the GPU address space, and if it's not available in there, then it fails, right? But that was not available for it. No. So tool is quite simplistic, I would say. It's written in Python. There's no compiler underneath. Nothing fancy. It's it's like a string translation from OpenACC statements into OpenMP statements, right? So it's basically composed in three components. The first one is parser, basically reads the source application and extracts the OpenACC statements, and to each of those, it associates to information regarding to the location into the source code, and adds that into a hash that is later used in the migration and code generation stages. Migration basically turns the translation of each of the OpenACC statements into OpenMP statements. We'll see later on how this translation is done. It's very simplistic. And also considers for some additional knobs that the tool can receive, right? So for instance, at this point in time, not all compiler supports OpenMP 5.2, for instance, or 5.1. So we have some knobs that allow us to tell, okay, we have 5.0 support, so we have this functionality available, or we don't have that functionality available, or other functionalities for support like support for asynchronism. So when doing the migration, the tool is also capable of changing the translation based upon these knobs. Finally, the last stage is once the statements have been converted, the code generation phase basically writes those translated statements into the original file, basically extends the code with the OpenMP standard statements. It also adds some if-defs if you're interested in, and it also creates a report with some information regarding the translation. It tells you it gives you some information regarding what has been converted, and if there were any issues with the translation, right? So this is the translation from the OpenACC to OpenMP regarding the construct. Well, this is mostly one-on-one translation. The only one that we'll cover later is regarding the kernels construct. And that's also interesting to mention the host data, which is typically used in MPI supporting GPU data migration, right? So we'll cover that later for kernels. The clauses. For the clauses, I would like to mention, let's go from top to bottom, the async clause. So since the compiler support, initially the async clause was a bit hacky, we decided to go into to either support the conversion of the async clause into an await, or to consider the possibility of not converting or not having asynchronism on the final translation. We are now adding support for asynchronous or the async with an optional parameter, which is this X, which basically refers to which CUDA stream you have to wait on. We are working to implement that on top of dependencies, right? And similarly for wait, and related to that, wait X has also to wait for the dependency, right? It's also interesting to mention the default present, which is converted into that long thing on default map for aggregates, pointers, and also locatables for Fortran. That is for OpenMP 5.1. If compiler supports 5.0, then implicit mapping rules are applied, right? And similarly for present, so if compiler supports OpenMP 5.1, the present clause is converted into map present alloc. Map present alloc, yeah. Otherwise, it's turned typically into map alloc. So there are a few limitations when converting OpenACC into OpenMP. I will mention, I think, that the three that are more important. The first one is regarding the kernels. And here it comes the typical comparison between OpenACC and OpenMP. People say the describe and prescribe difference between them. The thing is that in OpenACC, the kernels construct tells the compiler, try to identify parallelism within the code, and if it's worth it, and you expect that the code can take advantage if you offload that, then offload it. And there's nothing similar in that. Right? So in OpenMP, you say either this goes into the target or it is parallel or whatever. So by default, what the tool does is it translates this kernels construct into target regions, and that means that this runs that runs serially in the device, right? Our only exception is when the kernels construct in the OpenACC, it's combined with the loop construct. Then in that particular case, we know that that particular region, enclosed region, can go in parallel. So if we take advantage of this, we did some sort of extension into the tool that basically is able to have, well, it has some sort of look ahead, if one can say that in this way, in the sense that if we identify a kernel regions and we observe some ACC loops within the region, what it does, it converts those ACC regions, those ACC loops into real parallel offload regions, right? So in this case, for instance, we only had the OMP target and target at the very beginning and at the very end. But since we have these explicit loops with ACC loop, we know that we can convert that into OMP target teams loop. Same happens with the loop at the very bottom. And then in the middle, the statements that happens in this other code that marked with ACC loop, that happens also in the device. but in serial, right? Other limitations or and potential workarounds. First thing is related to performance, hardware binding clauses. This is something that I've been asked several times, and I have to insist that the fact that performance is not of the scope of the tool, even though we had so many questions, I tried to implement the translation for the gang worker and vector from OpenACC into the OpenMP binding counterparts, which are teams, threads, and SIMD. Question that one may consider is, okay, what does it make sense? Does it make sense if we had this running on a particular hardware vendor, and if I turn it to a different hardware vendor, does it make sense these numbers that I'm setting for number of gangs, number of workers, number of vectors, or teams, threads, and SIMD? Who knows, right? So the tool is able to translate those just for the sake of, okay, you want to check whether this is giving you best performance than the default values, so you can check those. One of the things that we cannot translate is SIMD, in this case, vector or SIMD, because what I'm showing here, this Pragma ACC loop vector, which has a nested Pragma ACC loop gang, which could be something like first the SIMD, and then we have a nested OMP target teams, right? This is something not legal from the OpenMP point of view. So this is why the SIMD construct it's not converted by the tool. Another thing that we found out while playing with different applications is the fact that OpenACC supported the mapping of multidimensional and non-continuous data. Right? This is something that it was interesting to see that they supported, but OpenMP does not. So the tool, there's a node that you can request to convert this sort of a statement, like here, this ACC enter data copy in, where we have these 3 dimensions from the array v3, and it generates this code. So we have this 3 nested loop that basically does the data mapping that is similar to the previous one. This is only implemented on C and C++ at the moment. I'm thinking how to implement this in Fortran. But I'm considering how to also an alternative, which would be of the use of the mappers, the declare mappers. I have not a particular clear idea of how to implement that, but this is something I'm considering to implement. Okay. That would also make easy the implementation for the conversion for Fortran. So we tested the tool in a number of mini applications. So we have 2 benchmarks from Spec Excel, and we also tested that on Pod3D and Cloverleaf. So we have a mixture of C and Fortran, and applications that range from 1,000 lines to about 11,000 lines. And these were tested on 2 different systems. The first one was using some NVIDIA accelerators. The other one was on a laptop-based machine with some integrated GPU. And the findings or the results for these executions were like that. So here, what we see is the performance results for system 1. And I know that I mentioned that performance was not the objective of the tool, but we thought that this could be interesting for the discussion and presentation of the tool. So what we have here are the performance results for the NVIDIA system. The pink line, the pink bar refers to the OpenMP results. So that is the baseline. From what I'm showing here, on orange, it's the OpenACC. It's the time it takes. The relative execution time to OpenMP. Blue bar refers to the translated version of the OpenACC, and the yellow one means to this translated OpenACC plus some additional optimizations that I will mention. So first thing that we see is that OpenACC typically outperforms the OpenMP implementation. this is initially was well, we could say, okay, maybe NVIDIA compiler is far more better for OpenACC than OpenMP. But when we were looking into the blue bar, we were looking into the translated version, we were a bit surprised to see that the translated OpenACC version was faster than the OpenMP original one. And we were looking into the code, and we observed that, that this particular benchmark, the order of the loops was different in the OpenMP and the OpenACC variants. And the thing is that that would explain that the performance improvement from 1 to 0.6, right? So it's about 60% faster. One of the things that I really like from compilers, as I said before, is the fact that one can ask the compiler, give me some sort of optimization report of what you're doing. And there we noticed that the OpenACC compiler was very aggressive in applying collapsing. Collapsing in OpenMP is something that you have to explicitly request. So we thought, okay, what happens if we apply the same collapsing in the OpenMP translated version, right? In the OpenACC translated version, excuse me. So if we apply the same collapsing to the same statements as in OpenACC according to the NVIDIA compiler, so what we turn out that the relative execution time is 14 times more or less faster than the OpenMP initial version. It's about 5 times slower than the OpenACC variant, right? In CG, the second benchmark, the translation of the OpenACC into OpenMP, it's slower than the original OpenMP and the original OpenACC versions. But if we apply these collapses that we saw from the NVIDIA compiler and we apply them into the benchmark, into the translated version of the benchmark, then we achieve the same performance as in OpenACC. So what happens with the system with the integrated GPU? System with the integrated GPU, we observed that the translated version from OpenACC, it's somewhat slower than the OpenMP. But again, if we take those loops that we collapsed as suggested by the NVIDIA compiler, and we apply the collapse into the translated version, then we have, for BT, we have a better performance. And again, recall that in this case, that the loop order is different. So we are about 3 times faster than the OpenMP implementation. And for the CG benchmark, we are more or less in line in terms of performance. So now the interesting point here is the fact that possibly that the loop collapsing, that the loop close could be somewhat improved or extended in the OpenMP. And it's also, I would like to mention that the spec Axel folks have changed also the OpenMP implementation for the benchmark, and they have adopted the loop order as in the OpenACC version. So for Pod3D and Cloverleaf, the story is a bit different, right? So Pod3D uses this host data construct. As I said, this is for GPU-enabled MMPI system. So on NVIDIA, using NVIDIA HPC SDK 22.2, we failed to generate the binary. And for Intel, we were able to run it, but we don't have the OpenMP variant to compare against. So unfortunately, we don't have numbers. For Cloverleaf, so this experimental feature that I was mentioning to translate the kernel's construct didn't work out of the box. So I had to go into different places and modify the code. Also, the map type present is not supported on NVIDIA HPC SDK, so it was translated into mapalg. And if we take all into consideration, the migrated version is about 9% slower than the OpenACC variant. And for the Intel, in this case, for the Intel systems, and this is an integrated GPU and it's not meant for HPC, and it doesn't have the double precision computation, it took ages to finalize, right? So in fact, I decided to control-C the execution because it took too long. So in conclusion, we believe that the features included in OpenMP 5.0 and that's beyond the loop construct and also the present clause, and that includes the API for that has been added recently in the 5 specification. That's a good thing for the translation of OpenACC code into OpenMP. There are some functionalities which cannot be mimicked. Possibly we could discuss whether some of these could be integrated into OpenMP. That's a thing we can discuss. And we have shown that number of benchmarks have been ported automatically. And performance portability is an orthogonal issue here. But as I said, we could consider the OpenACC statements that could be used as hints, but I'm not sure that in all the cases could translate into good performance. So in the future, we are considering to, we are working on the translating for the asynchronous mechanism, specifically for this async clause with this optional parameter by using depths. That's something that we're working on right now, and also for the mapping of user-defined types. And I was suggested by a colleague that possibly we could use also this sort of translation mechanism to convert some APIs such as BLAS. So for instance, we have this CUDA BLAS, we can convert them into a different implementation. So that's something that we're also considering. And that would be the end of my talk.
Thanks for the talk. So the first question that comes to mind without having read the paper beforehand is, why do we need another tool? Why couldn't we use CLAC?
Okay. So Clang is for C only, right?
So the answer is Fortran?
Yes.
But you also support C and C++ here.
You also support C and C++.
So you also build C support, right?
Yeah.
Okay.
So this is for C, C++. Yeah.
All right. And
so I know that the competition has, for instance, AMD has the GPU4, which is able to convert or to migrate OpenACC into OpenMP. Right? So there is, yeah, I know. And there are others who have converted OpenACC to OpenMP when using C, right? But they are also restricted to OpenMP4.
Okay.
So this is a mixture of everything. So in compiler folks, we're strongly suggesting to use the loops construct. And we thought that it was a good idea to have everything that we could have at the latest version for everything. And we could also convert not only C or Fortran, but all of them.
Okay. And follow like a completely different question.
Yeah, sure.
So the streams, async and wait with the dependencies, what is the problem with that? I mean, isn't that fairly trivial? With the, like supporting streams through dependencies?
Yeah, that's a very good question. That's a very good question. So the thing is that, at least for our compiler, support for dependencies on target regions has been a thing that has been evolving. And it wasn't clear to me how to express that initially. So I had to have a number of discussions with compiler folks and OpenMP related folks, and they had to. I was working with that, and I wasn't in time to get that version for the paper.
Okay.
So this is something that we are polishing, but that should be done soon.
Sounds good.
Great.
Okay, cool.
Thanks for the talk. I would have one simple question. You mentioned that, or maybe I understand quite well, the translation tool was written in Python, yeah?
Yeah.
Did you use any existing tool for parsing and stuff like that, or everything was built manually?
Everything was built manually. So To be honest, initially we were looking into other implementations. So there was a tool by Nicole Romero that was on the same line. So it was a Python tool, but it was somewhat simplistic. It was to use using dictionaries to convert from one sort of statement to another one. We also took a look at GPU4. I know that they have some sort of advanced, I would say, parser. That was a bit too big for the investment that we wanted to do, and for the idea that we also wanted to support C, and that we also wanted to generate loop or use OpenMP5. So this is why we initially discarded working on that or using that as a base point.
Okay, thank you.
Okay, Deepak, I think we also have Greg connected that raised the hand. So, Greg?
Yes. Could you just explain again why you had to do the manual collapse? Is it because the translator didn't have the collapse in it, or some other reason, or can you explain why you had to do, and maybe you can go back to that chart that showed that the performance improvement when you manually collapsed? Why did you have to manually collapse?
I had to manually collapse because in OpenACC, at least the OpenACC compiler from NVIDIA HPC 22.2, they apply collapse automatically, right? So the compiler detects that that code region can be collapsed and that they can get benefit. In OpenMP, for getting collapse, you have to explicitly request for collapse. And that is something that was not on the code. So in the OpenACC statement, there was no information at all related to the collapse request. That was done automatically by the compiler. So,
I see.
The tool cannot see that it will apply the collapse. So it translates the same thing in OpenACC into OpenMP, and then what happens is that OpenMP doesn't apply.
All right. Is there a newer version of the spec Excel that has the collapse in it for OpenACC?
Can you repeat that, please?
Is there a newer version of spec Excel that will have the collapse in it for OpenACC instead of doing it automatically, have it annotated?
No. So they have annotations for that. The thing is that the compiler decided to do it in its own. So it automatically decides to collapse it.
Okay, that answers my question. Thank you.
Sorry. ACC. No. So what they've done is they have changed the order of the loop. So there are two things here. First one, which is this, the fact that the translated OpenACC version for the benchmark is even faster than the OpenMP, right? So this is somewhat, it was surprising at the very beginning, is the fact that the order of the loops is different on the two versions, right? And the other fact comes from this, that the collapse clause, it's not applied automatically, but the OpenACC compiler does.
On slide 13, you had an example which you said was a little tricky. It looked like it was maybe a multi-dimensional array, or perhaps they're like an array of pointers. I'm not sure exactly what how V3 is being declared. Rather than mappers, you might consider using iterators.
Okay.
That was added, I think, in 5.1, and I think that might be a way this could be implemented in OpenMP.
Okay, thanks. I'll take a look at that.
And then you had on slide 19 post data construct, and you said that you translate that to target update. Seems to me like that would be more naturally converted to a target data with a use device pointer or use device adder clauses, which makes the device variables essentially available on the host.
Yeah, but the thing is, if you don't have an MPI implementation that supports GPU addresses, then does it make sense to use that? Possibly you want a staging buffer on the host and pass that to MPI. So yes, I did omit that when I presented the thing, okay. But in this case, it's not a limitation of the tool. It's the fact that you have a good software stack that is able to support that. So you can have the GPU pointer, but if you can do that, anything with that.
Thank you. Thanks for the talk again. One more question. So you mentioned it's not compiler technology. So it sounds like you would like replace every instance of Pragma ACC gang to Pragma OMP teams, for instance. So like a purely syntactic change, but you also have, it seems to know that which Pragma is nested inside, which goes a bit beyond just syntactic changes. And for the example with the mapping, it seems to know what the types is.
No, there's no information at all.
Okay. My question is like, what other kind of non-just syntactic information does the translator use? Like, as I said, like nesting. Is there anything else? Like it could see like if there's perfectly nested loops, it could like collapse them automatically. No. It's also not something. Is there anything else that it does?
No, it's almost a straight conversion and a bit of this look ahead that I mentioned before, but there's nothing much in there, at least yet.
Okay. So what are their plans?
Well, that would depend on request, based on request, right? So this was just to help on translating some, in this particular case, Fortran applications from OpenACC to OpenMP. And I'm planning to support the tool, but based on request. So if there's interest of a particular thing that I can implement, that I would be happy to do that.
Thank you.
So you mentioned the collapsing by the OpenACC compiler. Were those loops kind of strictly nested with OpenACC loop annotations, and it basically just said loop, and that was collapsed, or was it more complicated than that?
I don't recall right now. I think that there was a single OpenACC statement.
Okay.
And the OpenACC optimizer decided to collapse the subsequent or the nested loops. And I think, if I remember correctly, they were perfect nested loops.
But the nested loop was not annotated.
No.
Okay. Yeah. I'm trying to figure out how much magic we need to copy that behavior. And there's a lot of magic needed.
Well, that's something that I was discussing with some colleagues, whether we could consider adding some automatic collapsing into the OpenMP specification, right? So whether we could have, let's say, collapse auto, and you let the compiler decide how many levels you want to collapse, or maybe we can even go more freely and say, okay, we have this loop, and then the compiler can do the collapse automatically. But I'm not sure whether that would be in the OpenMP nature.
The thing is, we don't need a collapse auto per se. If the compiler can figure out collapsing is legal, it can just do it. The reason we need collapse with a number in the first place is so we don't have to figure out if it's legal. The user tells us, right? And I mean, it also tells us how many we should collapse for like performance reasons, but we would need some kind of legality argument. That is the hard part, right? Mm-hmm. And if all the loops would be marked as, yeah, this is perfectly parallel, on loop or whatever, makes it way easier to auto collapse them after the fact. But if they first have to determine if it's legal.
Well, for some loops, it's somewhat easy to have some dependency, if you don't see if that's legal or not.
Yeah. Sure.
Yeah.
I'll take your word for it.
I'm not a compiler folks. So for me, it seems this has been in the compiler side for years and years. Right? I agree that's a very difficult thing to evaluate.
So this was all done with the NVIDIA compiler, is that right?
No. So results from this slide are from the NVIDIA compiler. These are for NVIDIA compiler, and these ones are for the Intel compiler, right? And on system 1 we use NVIDIA hardware, but system 2 is for Intel hardware. So we use the Intel compiler.
So the translation translated all of the OpenACC construct, or was the resulting source file having a combination of OpenACC and OpenMP?
So the tool, you can tell the tool whether you want to keep the original OpenACC statements, whether you want to have both OpenACC and OpenMP statements, and whether you want to protect them with if-def, for instance.
Okay.
So you can play with that. One thing that we are working now is also on the possibility that the input application not only has OpenACC, but also has OpenMP for the host. And that would be somewhat tricky, because what happens if the portion of code is impacted by the OpenACC statement and also the host statement? So that means that the translation of the OpenACC statement would enter in conflict possibly with the OpenMP for the host. So we were discussing with the possibility of using metadirectives for that. So the tool could recognize the OpenMP statements and say, okay, this is for the host, and what I'm adding into you is for the device. Something like that.
Is there a plan to publicly release this tool?
It's already public.
Oh, okay.
Yeah, it's figured out.
Okay, then thank you again to the speaker.
Questions from the session chair?
Actually, you stole my question, because I don't understand why you did this outside the compiler, because this is preventing you from doing a lot of optimizations and getting actual performance.
Well, it's not preventing you. So you have the source, you can do whatever you want.
Yeah, but you have a lot of logic already implemented in the compiler to do analysis.
Okay.
And you are not exploiting that option. So are you planning to, when you have Flang available in LLVM, are you planning to migrate this?
That's the point.
Okay.
So, yeah, but what if you don't use Flang? Yeah. So, yeah.
Okay, then. Thank you.
So much.
Thank you. And I guess I'm gonna be saying that's it for today, and we see each other tomorrow again.